So my next question is, let G be a infinite cyclic group, then determine the automorphism of G. So I take, let G generated by A be a infinite cyclic group. So my question is to determine the automorphism of the G. So let T belongs to automorphism of G. So it means T is 1 on 2 as well as homomorphism. And my claim is G is also generated by TA. So G is also generated by TA. So in that case, let X is some element belongs to G and T mapping from G to G. This mapping is a onto. So every element has pre-image. So there exists Y belongs to G such that this X is equal to T of Y. Now what is Y? So since Y is element of G and G is generated by, so since Y is element of G and G is generated by A, so it implies from this, it implies Y is equal to A raised to power R. So this is for some integer, R, this values. So it implies what is X? So X is equal to T of Y. Now substitute the value of Y. So this is T of A raised to power R. Now T is homomorphism. So this can be written as T of A raised to power R. So any member of G can be written as the form of T of A raised to power R. So it implies G is also generated by TA. It means G is also generated by T of A. We can also say that TA is a generator of G. So it implies this TA is a generator of a cyclic group G. So it is a generator of cyclic group G. Now what is G? G is infinite cyclic group. So it has two generator, either A or it inverse. So since it is a infinite cyclic group, then T has two choices. T has two choices, either TA is equal to A or A inverse. So it has two choices, either it is A and A inverse. Then it means order of automorphism of G is cannot greater than 2. So it means it is a less than equal to 2. So this is equation number 1. So what we get? We get the order of automorphism of G is always less than equal to 2. Now second part, to prove that its order is always greater than equal to 2, then it means order of automorphism of G is equal to 2. Now define a second map, define T from G to G by T of x, which is equal to x inverse for every x belongs to G. For every x belongs to G. Now this T is not identity. This T is not identity because suppose if this T is a identity operator, then it implies T of x is equal to x, and it implies x inverse is equal to x, and it implies x square is equal to identity. It implies x square is identity. So it implies order of x divide 2. It implies order of x is a finite, but order of G is infinite. So order of x cannot be finite. So it implies which is not possible, which is impossible, since order of G is infinite. Order of G is infinite. So it implies T is not equal to identity. So it means T has two automorphism. One is identity, second is this T. So it implies G has at least two automorphism. If G has at least two automorphism, so it implies order of automorphism of G is greater than equal to 2. So which is equation number 2. So from 1 and 2 we get order of automorphism of G which is equal to 2. So what are these automorphism? So it means automorphism of G, it consisting two automorphism. One is identity and second is T, and T is a automorphism which goes to its inverse. So where T is automorphism, where T of x which is equal to x inverse for every x belongs to G. So it means when G is cyclic group of infinite order, so it has two automorphism. One is identity and second is T. So this is very important to find the automorphism of this values, right? So in this case, we can find the automorphism of this. Now, in this, for example, if we have, for example, by using this result, so automorphism of Z, which is isomorphic to Z2. isomorphic to Z2. Now what is this? Z is cyclic group. So Z is infinite cyclic group. So if it is infinite cyclic group, so it has two generator, 1 and -1. If it has two generator, then we know that automorphism of Z, that is isomorphic to Z2. So this is some example related to this. Now, if we have the cyclic group of finite order, so already we did a question. Now, the next question is, now this is in GNDU 2014 and many other years. So if we have, if G is cyclic group of order n, suppose it is a cyclic group of order n, then determine the automorphism of G. So remember that there are only two automorphisms when G is a cyclic group of infinite order. Now here it is a cyclic group of order n, यानी कि finite order. Solution of this result. Now what is G? G is generated by A. So it is a finite cyclic group. So as we know that order of G and order of generator are equal, so this is equal to n. So I write it as equation number 1. Now if this is equal to this values, now we know that as in previous part, suppose T belongs to automorphism of G. If T belongs to automorphism of G, and we prove in the previous example that TA is also generator of G, generator of this finite cyclic group G. T is also generator and T is also generator of G. Now how we can find the generator of a cyclic group of order n? So generator of cyclic group of order n are phi n. So what is phi n? So phi n, which is equal to all m integer, such that GCD of m is equal to 1. And what is m? M is less than n and greater than equal to 1. So this values, what is m? M is integer. So this is a phi n, which is a Euler function. So these are the number of generator of the cyclic group of order n. So it implies TA has phi n choices, because here the number of generator are phi n. So it means it has phi n choices. So it has phi n choices. So it implies, what is this mean? Order of automorphism of G is always less than equal to phi n, right? So which is a equation number 1. Suppose it is equation number 1. Now to prove this automorphism is greater than equal to phi n, so we define a mapping Tm, this Tm that is related to this. It is from G to G, and this is defined by Tm of x, which is x raised to power m. This. What is m? So m belongs to phi n, set of phi n. Ja, we can say that where GCD of m and n is equal to 1 and 1 less than equal to m less than n. So this is my equation number 2. Now this map are automorphism, this map are homomorphism, this map are homomorphism, and always on to, and this is a 1-1. So these map are homomorphism. So it implies clearly there is no need to prove. Clearly Tm belongs to automorphism of G. But here my aim is to prove that all these Tm are distinct. So here my aim is to prove that all the Tm are distinct. If all the Tm are distinct, to prove that, I take to prove all Tm are distinct. All Tm are distinct. Now to prove this, if I take Tp and Tq, they are equal. What is P? P and Q are where P is GCD with N equal to 1 and GCD of Q with N is equal to 1 and P is less than N greater than equal to 1, Q is less than N greater than equal to 1. So I take 2 mapping and suppose these are equal. To prove that it is a distinct, so I take these are equal. If these are equal, then it implies Tp of A, which is equal to Tq of A. What is A? A is a generator of our cyclic group. Then by definition, what it becomes? It becomes A raised to power P, which is equal to A raised to power Q. So what it becomes? It becomes A raised to power P minus Q, which is equal to identity. So it implies A raised to power P minus Q, and this is equal to identity. So again by definition, order of A divide P minus Q, right? So what is order of A, which is N? N divide P minus Q, this values. So what is P? Since P is less than N and Q is less than N, so it means P minus Q is always less than N, but here it divides these values. So it is possible when this value will be 0. So this is possible when this value will be 0, right? Or we can also say that, but we take P and Q are distinct. So we can also say that it implies n is this is possible since p minus q is less than 0. So it implies p minus q equal to 0. It implies p equal to q. So what it means? It means all TMs are distinct. So all TM are distinct. So what is the number of these TMs? These are 5n. So if they are distinct, then it means order of automorphism of G, so which is greater than equal to phi n, this values. So I write it as equation number 3. If I combine these equations 1 and 3, so what we get? Order of automorphism of G, so which is equal to phi n. So what is the automorphism of these values? So this set consisting automorphism of G, which is of this kind, which is one is identity and second is, so this is a identity one mapping. So this is of this kind, t raised to power, this is t m, such that GCD of m and n, this is equal to 1. And what is m? So m is greater than equal to 1 and less than n. So when it will become 1, so it is a identity. So this is a automorphism of G. Where what is the formula of TMX? So formula is Tm. So I write it once again. So it is a set of Tm such that Tm of x, which is equal to x raised to power m, GCD of m and n equal to 1, 1 less than equal to m less than n for every x belongs to G. So this is a set of automorphism of order of group of order n, of finite group of order n. So remember that. So this is a set of automorphism. Now from this we can also prove that this group is isomorphic to group of integer multiplication modulo n. So this group is automorphism of G. This group is isomorphic to group of integer modulo n. So let Gn. So what is Gn? Gn is a group of integers multiplication modulo n. So its values are all m such that GCD of mn, which is equal to 1, and this value 1 which is less than equal to m less than n. So what is this? Also we may write it as u of n. So what is it? It is a group of integers, in multiplication modulo n. So modulo n. So that is isomorphic to these values, un. We can also say that Zn, because it is a cyclic group isomorphic to Zn. So also we may write it as it is isomorphic to Zn. Now, to prove this, what we get, now define a mapping. So define a map phi which is from automorphism of G to this Gn. Also we can also write it as U of n, right? Also we can write it as U of n. Now this mapping is defined by what is the mapping phi of t raised to power m, and this value is equal to, so here this is Tm, this value is Tm, this is equal to m. For every m which is a GCD with n is equal to 1 and 1 less than equal to m less than n. Now to prove this is a isomorphism, so prove that it is a homomorphism, then 1 1 and then on to. So first, to prove it is a homomorphism, so to prove it is a homomorphism, I take two mapping TP and TQ which belongs to automorphism of G. So this mapping. Now what is phi, which is a TP and TQ, this values. Now the condition are same, P lies between 1 and n, similarly Q and GCD with n are equal. So that condition is, I write 1 less than equal to P less than n, similarly 1 less than equal to Q less than n, GCD of Pn is equal to 1 and GCD of Qn is equal to 1. Remember that. So this mapping can be written as phi, this is TP and TQ. This mapping is TP and TQ. Now check that what its value. So TP into TQ of x, this values, this can be written as TP x raised to power q. This is x raised to power q. So again operated by p. So this will become x q and then raised to power p, this values. So what it becomes? So it becomes x p multiplication modulo q. So this values p multiplication modulo q of x. So this values, so this values x raised to power this. So what is this? It is basically t p multiplication modulo of q with respect to x. So this is by using that result. So phi of this values, what is this? It is a t by using this result multiplication modulo q. This value by definition p into q, this p into q multiplication modulo. So that is binary composition on right hand side. So what is phi of TP into phi of TQ, So what it means? It means this mapping phi is homomorphism. So this is my first step, homomorphism. So this is a phi is homomorphism. Now after that it should be 1 1 and then onto. So again the same element I am taking. So this is phi Tp, which is equal to phi Tq, this values. Now what it becomes? It becomes, just substitute its value, P is equal to Q. If P is equal to Q, so it implies Tp, which is equal to Tq. So what it means? It means this phi mapping is 1 1. This phi mapping is 1 1. After that, to prove it is a onto. So what it means? For every M belongs to un ja gn. So this values. So what the definition, if it belongs to this values, so GCD of Mn is equal to 1, number 1. Second is 1 less than equal to M less than N. This is second condition. So both are satisfied. So it implies Tm, which belongs to, which is automorphism of G. As we prove that, we can find, because it is a generator, so we prove that a Tm belongs to automorphism of G such that phi of Tm, so which is equal to M. So this point, this integer has pre-image this. So it means this mapping phi is onto. So this mapping is phi is onto. So it is a homomorphism 1 1 and onto. So it means automorphism of G, which is isomorphic to Zn ja Gn. This is a isomorphic to Gn, right? So this, in this way we can find the automorphism of G. So which kind of automorphism of any set? So this is the automorphism of the G. So this value we can find that. Now after doing this two question, so if we have a some cyclic group of infinite order, suppose we have a this cyclic group Z, which is a cyclic group of infinite order, and if we have a cyclic group of order n, then that is isomorphic to, that is automorphism of, that of G is isomorphic to Zn, ja we can also say that Un. So this is a, in case of multiplication modulo, and when it is in addition. Now after going to this, we will discuss the some important question. So what is the statement of question is, if f is from G to G, this is some mapping from G to G, such that f of A, which is A raised to power n, and this mapping is an automorphism. This mapping is an automorphism. So that is a given. Okay, this mapping is a automorphism. Then show that A raised to power n minus 1 belongs to center of G for every A belongs to G. So this belongs to center of G for every A belongs to G. So A raised to power n minus 1, it belongs to center of G. So remember this values. Now, to prove this result, we consider solution. We consider f which is of A inverse xa, these values. Now, what is f? F is a automorphism. So I consider A raised to power minus n x, and this is A raised to power n. Now what is f? F is a automorphism. So by using the definition, this can be written as A raised to power minus n x and A raised to power n. This is raised to power n. Now we prove one result in the previous chapter. A inverse xa raised to power n can be written as A inverse x raised to power n into A. So this value will become A minus n x raised to power n A raised to power n. These values. Now, in order to simplify by using the definition of automorphism, so this is a f of A raised to power minus 1, and this is f of x, and this is f of A. So just using this definition. When we use this definition, and since f is a automorphism, so it is a homomorphism, so this is A inverse x into A, this values. Now again, because f is a automorphism, so it is a 1 1. So 1 1 means if the image are same, then the element are also equal. So A raised to power minus n x raised to power A raised to power n. So this value is equal to A inverse into xa, this values. A raised to power this values. Now this can be written as A when we multiply by A on both sides. So this can be written as A raised to power n minus 1 into x, and similarly this is A n minus 1 which is equal to x for every x belongs to G. So what it means, this is shifted to this values. So this value is equal to x A raised to power n minus 1, and this is A raised to power n minus 1 into x for every x belongs to G. What it means? It commute with every element of G. If it commute with every element of G, so it means A raised to power n minus 1, it belongs to center of G. So which